Hi, everyone. Welcome back to session 3 of our Data Science Workflows in JavaScript workshop series. Excited to see you, whether you've been here for all the sessions so far or if it's your first time. I'm really excited for you to, call in and follow along with the cool work we're going to be doing in JavaScript Plus today. So I'll do brief introductions. Hello, welcome. I'm Allison Horst. I am a data scientist advocate here at Observable. We're also joined by Robert Casara, a data visualization developer at Observable, and Wayne Sutton, our community and events manager at Observable. So if you have questions throughout the day today, we will all be watching the questions. Robert and Wayne are both behind the scenes, ready to respond to your questions. So feel free to post those in the chat that you see where you're streaming this. Or if you've joined our community Slack, which I highly recommend, it's a great place to join a community of other folks that are learning JavaScript and Observable Plot and D3. So go ahead and join us there. And that is also an awesome place where you can ask your questions. So a few logistics, these will sound familiar if you've been in the first couple of sessions. We are in session 3 of 3. There is a certificate available at the end of this workshop series if you've been following along, and you complete a short task that we're going to post actually immediately after this session is over. Then you can get a certificate that you'll be able to share. You do, to participate, need an Observable account. That'll allow you to fork and save the work that you do today. Already covered the questions. And all sessions are being recorded, and all keys and notebooks associated with this entire workshop series will be miss anything. And also, as a reminder, we're going to take several 5-minute breaks throughout the day today, since 2 hours as a full continuous block is kind of long to be just writing code nonstop, which is most of what we're going to be doing today. These are really hands-on coding sessions. Hi, everyone who's saying hi in the chat. It's awesome to see familiar names and faces. All right. So in the last 2 sessions, we have learned a bunch of different methods and tools at different phases of the data science workflow or life cycle, like how to attach local files, how to load in data from remote resources, how to use imports to get information from other notebooks in Observable, how to insert data using the data table cell. We also did some tidying and wrangling with array methods like map and filter, but also with Arcaro. We could also do some right in the data table cell, which is cool. Today, we're going to be adding some SQL. Bait and switch, just a little bit, I promise. We did some visualization. We're going to continue that today with the chart cell and with Observable Plot. And then we have been doing some modeling using methods that exist in the ml.js package. And that's what we're going to use for principal component analysis today. We've also learned how to share notebooks with folks just by sharing the URL, how to embed content. And today we're going to be adding how to actually communicate with people by adding them to your notebook so that you could collaborate with them and comment right in notebooks. We're also going to add a few more tools kind of dispersed around this workflow. We're going to see how we can work between SQL and JavaScript cells. So if it's your first time writing a little bit of SQL, don't worry, that's great. Welcome. We're going to do some more Observable Plot. We're going to use import with to reuse community contributions. So we're going to be adding a few new skills and learning about principal component analysis for when we have multidimensional complex data, and try to glean as much information as we can from that data in a more manageable for us number of dimensions. So the learning objectives for today are to create a database in a notebook. That's going to be cool. We are going to wrangle data in a SQL cell. Then we're going to take the output of that query and do some exploratory data visualization in JavaScript, seeing that we can seamlessly work between the two. We'll do principal component analysis and then visualize principal component scores and loadings in a biplot. We'll remind ourselves the different ways that we could share outputs from an observable notebook. And then Robert and I are going to do a quick demo of how you can add a coworker as a collaborator in a notebook and truly do like multiplayer simultaneous editing right in the same notebook, and have discussions and comments right in notebook too. Then we'll do a little wrap up where I introduce the assignment that you can complete to get the certificate at the end. All right, so today, a little introduction to the data set that we're going to be using. So far, we've been using charismatic creatures. We're switching over to really critical abiotic data that has meteorological information from rocky shores on Brazil's southeastern coast, just west of Rio. So this is a really cool data set that is shared openly, which I always have such immense appreciation for, by Marcos da Silva et al., who published this in the Data in Brief journal in 2019, which, by the way, if you're looking for data to like just do data exploration and analysis as practice, Data in Brief has a ton of really cool openly shared data resources and accompanying methods that you can follow along with. But what this team has done is they have collected from different online publicly available resources a bunch of variables about things like air temperature and humidity, and also sea information, so sea surface temperatures, salinity, etc. So they have combined all of this data so that it can be used in the same place. And one thing that I really appreciate about this data set is the author's recognition that it was important to do this, because even if data exists in dispersed places, that doesn't make it easily accessible or usable or discoverable by people who might need to understand it or be impacted by it. So they specifically call out that there is this like gap for this region on the southeastern Brazilian coast, near Marcosado Beach. That along this stretch there was this data gap, where even though the data existed, it was not accessible for researchers or for local people who want information about the climatic and ocean conditions near where they are that impact them. And so they have collected this aggregate data set and then showed some analysis with it that we are going to continue working with, to start exploring changes in seasonality along this stretch of the Brazilian coast. So that's the data set that we have to look forward to today, with much appreciation to the authors for aggregating it and then also openly sharing it. All right. Let's go ahead and get started. Let's jump into the notebook. So we are going to share in the chat a follow along version of the notebook, which will look like this. So this is the follow along version of the notebook. And if you want to follow along, which hopefully y'all do, which means you'll be writing your own code, then what you want to do is fork this notebook to create your own copy in your own account. So the way that you fork is up in the top right of your notebook. There's this little fork icon that I'm hovering over here. And if you click on that, what that's going to do is it's going to make your own copy of this notebook in your account, which means that your changes are going to get saved. So I'll give everybody a minute to go ahead and make sure that you have a fork. If you have not signed up for an observable account, you can make edits in that notebook that we shared. We don't advise that because none of your changes will be saved. So like if you're working and then you refresh the notebook, all of your changes will be gone. So definitely you want to have an account and fork the notebook so that your changes are saved as you edit today. All right. Let's go ahead and start doing some coding. All right. So today what we're going to do is we are first going to work with data that's already attached. So we had in previous sessions, we had actually like attached a local file into our notebook, or we had read in a remote file using like D3 CSV. But today what we've done for the sake of time is we've already attached this data in your notebook. And what these are, so these two files that are showing up here, where notice we're using file attachment, calling the file name from those files that are attached in the files pane, that we could just drop more files in here if we wanted to. And then making sure that these are being parsed with different types. So when I look at this array of objects, if I expand this by clicking that left arrow, I can see that these are parsed. And the information in here includes things like a month, which is stored as a date, maximum and minimum air temperatures, information on humidity and air pressure, information on wind speed and direction, dew points. So we have this like meteorological data. So that's in one of the tables that's already attached for you. In the second table, we have data related to sea surface temperature, tide information, and salinity for those same months in the data set. So we have these kind of separate sea and air tables, but what if we want to work with these in combination? Well, we can absolutely use one of the methods that we've used so far. We could do joins right in plain JavaScript. We could join things in Arcaro. But what we're going to do is, let's say we're data analysts who are actually just like very, very happy working in SQL. A cool thing is that you can actually create databases right in your notebook and then write SQL queries on those databases so that you can work and do your data wrangling or analysis right in SQL. And the other thing that we'll see is whatever you do in SQL, you can take those outputs and then automatically use them in JavaScript cells to like make a visualization in Observable Plot. So let's go ahead and combine these. So using the DuckDB client, which lets us work in SQL using DuckDB right in the notebook, we are going to create a database, right? Like right now, these both only exist as these separate files as arrays, but it's not like a database where these are combined in one place with a schema that we could query the way that we might be used to. So to do that, I'm going to call this Marcasado DB for Marcasado database. And as a reminder, Marcasado is that a beach name in that stretch of rocky intertidal zone along Brazil's southeastern coast. So we're going to be using Marcasado to name a lot of these things. And the way that I can create a database, which I think is so cool, is I am going to use DuckDB client, the of method, and then within curly braces, I can give it the name of what I want the table to be called in this new database that I'm creating, and the array of objects that I want to make up that table. So here I'm going to say I want one table in this database to be called air, and that's going to be comprised of the Marcasado air array of objects. So I'm going to say Marcasado air. And then I'll have a comma, and then I'll say I want a second table in this database called C, which is just going to pull from Marcasado C. And this might not seem that magical like at first, but I think it's pretty amazing actually. So what we've done is we've created a database right in our notebook. So what I want to do is I'm going to go ahead and shrink this down and see if you can see. I'm going to move a thing over really quick. Okay, so now you can see I'm going to hide my face for a second too. So now you can see we made this database, but how can I actually check to see like, did I actually make something? If you go over to the databases pane, which is that little database stack icon in the right column, now you'll see that I have multiple database cells. So I can write SQL queries on regular arrays too, which we'll see. But I also have created this Marcasado DB DuckDB database. And if you click on this, and this is where I think this gets really nice, is if you click on that, it'll actually show you the schema for the database. So it shows you which tables are there. If you click on the table, it will show you what variables are in it. So this gives us a really quick way to explore what's in a database. I'll also say that we just created an in-notebook database, which is cool, but we have a bunch of built-in database connectors. So like the more common scenario would probably be that you're like connecting to your organization's database and like Snowflake or MongoDB. And so we have connectors for a lot of those databases where you can actually go ahead and set up the connection, and then you can right away start querying from those databases, which is pretty cool. But we've just created one. All right, so now that we've created our database, we're going to go ahead and start wrangling it. I present this as one option because there are a bunch of data analysts and data scientists where when you're working with a database, which is very common, that the language that you're using is SQL to do your queries and some analysis and wrangling. So I want to show that we can do that right in Notebook and then just like transfer those outputs into JavaScript cells. So what I'm going to do, here's a little summary of the variables, and this is what we're going to be doing. So we're going to combine data from both of these tables. So we want to get one array of objects that combines information about air and sea data from this Marcasato area. But what we want to do is we only want to keep a sum of the variables for each of these data sets. From the air table, we want to keep month, we want to keep the mean pressure, wind speed, PAR, which is photoactive radiation in Einstein units, the mean humidity and wind direction. And from the sea table in our new aggregate data, we want to keep information about the maximum tide, the minimum tide, the salinity, and the sea surface temperature. And what we're also going to do is we are also an important part of this paper that this data was published in was trying to identify distinct seasons based on this multivariate data. And so they, in their paper, described two distinct seasons, a hot and moist season from October to March, so months 10, 11, 12, 1, 2, 3, and a cold and dry season from April to September. So what we're going to do is we'll also add a new column that indicates the season based on what these authors have described, because we're going to come back to that later and ask ourselves, like, okay, when we look at information for across all of these variables, then does it appear like there are these distinct seasons within the data? So what I'm going to do here is go ahead and add a SQL cell. So this is something we haven't done in the workshop so far. So you still go to the add cell menu, which as a reminder, oh, and I can turn my face back on. All right. as a reminder, to add new content in an observable notebook, you're going to create any content you add in a cell. And a way that you can add new cells in a notebook is using the add cell menu, which you get to by clicking on the little plus sign in the left margin of your notebook. And that'll show up between any existing cells. So here, I'm going to, right below where it says add SQL cell here, I'll click on the add cell menu, and this is also searchable. So I'm going to start typing SQL, and you can see that we have this option for a database query. If I select this, this inserts a SQL cell for me, and then I can choose my data source, which for us is that Marcasato DB DuckDB database. So go ahead. I'm going to do that one more time in case that was quick. I'm going to go to my add cell menu by clicking this plus sign. I'm going to start typing SQL. The option that comes up is this SQL database query. Once I select that, a SQL cell is added that prompts me to select my data source. All right, so the data source that we're going to pick is our database that we've created. So I'm going to pick Marcasato DB, and then I can start just writing my SQL queries, and it's going to show the outcome of that query in a nice table immediately above. Again, if you've never written SQL before, that's all right. We're just going to do some kind of intro stuff. As a reminder, you also have the key. And we'll also share this cell, the actual text that we write in this cell in the chat once I'm done writing it, so that if you got lost with like a syntax thing, that you can still get caught up and follow along. So here, I'm going to use select, which is what we use to select variables. And if I use, for example, select asterisk, which in SQL is like everything, if I use select everything from air in that database, then I can see immediately above that cell shows up like everything as it existed in air already. But that is not what I want to do. What I want to do is I only want to select certain columns from each of my data sets. And then I want to join information from C to this air data. So that's what we're going to do next. We're going to do a little bit of this wrangling. So I'm going to talk through this, and then yeah, I'll just talk through this, and then again, the key is available, and we'll share this code. The first thing I'm going to do is I'm going to say select air month. Now, this is kind of a weird one, because like if you're just getting it from air, then why do you have to specify it's from air by doing air dot here? And that's because later on we're going to join with the C data, which also has a month column. And so we just want to pick one of those that is actually resulting in our final table. So we're going to select air month. We are going to do mean pressure. That's only in air, so I don't need to specify. Mean pressure, messing up my commas, PAR. You could write this differently. If you just want to do air month, comma, mean pressure, comma, par, comma, you could do that all in one line if you wanted to. I blame Paul Buffa for me adopting this organization. Mean humidity. We're doing wind direction and wind direction. Okay. And so if I run that, then I see that now I have these 5 variables from that air table that's in our database. But I don't just want those. What I want is I also want to join the C data to this and then just specify the variables that I want from C. But first I'm going to do the join. So first, after this, now that I have these variables that I want from air, I'm going to say I also want to join the C table that's also in my database. So we have access to it here. And then I'm going to say what variables we're joining on. And my just some awesome chat casting blame. That's funny. Okay, so we're joining C here, and we need to say like what variable we're joining by. And the thing that we're going to join by here is across both of these tables, the month is the actual variable that we're going to join things by. So this is going to let us have, for each month, we're going to have these atmospheric variables, and we're going to join to that the sea surface temperature and tide information and salinity for that same month. So we got to give it that variable. So what we're joining on here is the air month column is aligning with the C month column. And running this, and again, to run this, you can like just press shift return, or you can press this play button. But we can see it like nothing changed, which is kind of bizarre. And that's because we actually haven't said what we want to keep from C. We haven't indicated that we want to keep any of these variables from C. So what I'm going to do is keep adding in my select statement. I'm going to add C max tide. And again, this is from the joined database or the join table. So I'm specifying the table that it's from here. C min tide, C salinity, and C surface temperature. And that's C surface temp. So, and once I do that, now I can see that in my table immediately above, now these variables have actually been added and joined by month. So they align by month with that atmospheric data. Now we do a bunch more stuff here. So for example, what if I'm like, you know what? C surface temp is a long name. I would rather have that be renamed to SST. So I'm going to, if I wanted to rename things here, like sea surface temperature, I can use as, and then if I use as SST, then I can see when I scroll up now that sea surface temperature variable has been renamed to SST. So SQL is really nice for like combining things, renaming things, doing some wrangling. Is a really, really nice language. Just to like put a point on this, that as, because I walked through that kind of quickly, if I wanted to rename air month to like bananas, which I'm immediately going to revert, so don't feel like you need to follow, I would just do as bananas, and then I can see that that variable is now stored as bananas. That's not what I want. I'm going to keep the original variable name. All right. So now we have this join data for these variables that are of interest to us, but we don't have in here that variable on seasonality that we want that the authors had indicated. And as a reminder, they identified that October to March is this hot, moist, humid season. And April to September is this cool, dry season. So we're going to add a new column here, a new variable that stores a string, either hot, moist, or cool, dry, based on the value of the month, just the month piece in our month column. So if it's 10, 11, 12, or 1, 2, 3 for the month part of that month, then this new column should contain hot, moist. If it's a month that is April 4, 5, 6, 7, 8, 9, then that new column should contain cool, dry. And we're going to create this new column called season. So where we're going to do that is because we're adding a new column that we want to keep is still right in our select statement, and we're going to use a case when statement. Case when is a conditional statement where what is populated in our new column depends on a condition that we specify. So here I'm going to say case when, and then I'm going to use some really cool functions for working with dates and times in DuckDB. This one uses date part, which is going to pull just the month number from the month column here. So here I'm going to say if the date part, and then you tell it what part of the date you're interested in. So month, and then we'll give it the column from the month column. Sorry, I'll go do air month. So that's going to tell us, like, if it's January, this is going to be 1. If it's April, this is going to be 4. So if the month part from that month column exists in this sequence of values, so I'm going to give it this hot, moist sequence of values. So if it's month 10, 11, 12, 1, 2, or 3, then I want a new column to contain the string hot, moist. Otherwise, and that would be the case, the otherwise is if it's months 4, 5, 6, 7, 8, 9. Otherwise, I want it to contain cool, dry. And then I'm going to end that conditional statement because I could have additional like else statements here, but that puts an end to this. And then I need to give it the name of this new variable that I'm creating. Oops, and I think I need quotes around the seasons because it doesn't exist yet. What am I doing here? Near case, 1 second. Or near case. Is anybody seeing anything else cool, dry? All right. Yeah, this does not look like it's working. Let me see. Oh, thank you. Okay, thanks everybody. All right, teamwork makes the dream work. I made a mistake here, which is that I put my case when statement after the from clause. God, I love community support. This is great. Okay, thank you. So I made a mistake of putting this case when statement after this from. Excellent. Oh man, excellent, everybody. Okay, I'm gonna move this to after. So once I put that there, thanks everybody. Now now I have my updated table. Again, moving that case when to before the from. Now I have my updated table where I have this new season column added that has if it's months, if it's October, November, December, January, February, March, that I have this new column containing hot, moist. If it's any other column, then we have cool, dry. So, or if it's any other month, so if it's April, May, June, July, August, September, then we have this cool, dry column. All right, great teamwork, everybody. Thanks, y'all. Okay, so now we have our wrangle data done using some SQL. Cool. This is but we haven't named this. Like this doesn't currently have a name. I'm going to give this a name, which you can do so that we can work with it later. We can call the results of this query to use later on. So I'm going to call this Mar Casado. So that, again, that's right up in the cell just to the left of where you choose your source for the SQL cell. I'm going to name this Mar Casado, and then that is an array that I can use in a JavaScript cell later on. Now, just to show you that like we created this database and then we wrote a SQL query to do some, get some columns we wanted, do some wrangling and renaming, add a new column. You don't have to convert an array to a database in order to write SQL against it. So I'm just going to show an example here. You do not have to do this, but just to show an example of doing this without a database, I can choose the SQL cell and then I can choose an array as the source here too. So I can choose this array of objects that we just created, Mar Casado. And then I can just like write my SQL code from Mar Casado. And like I can write SQL against that array of objects too. So this gives me a really cool tool to like, if I'm happier in SQL, or if I'm working with data in a database and my team is using SQL, that I can work right in Notebook in SQL. But this gives me a seamless way to work between like an existing JavaScript array or data structure and putting that into a SQL cell, or taking what I've created in a SQL cell and then I can just continue working with that in my JavaScript later on, which is pretty cool. All right. We're pretty early on. So let's just do like a 4-minute break. Let's do 5. I feel better because we're starting at an odd time now. So we'll take a 5-minute break. We'll get back here at 9:38 Pacific time. Come back at 9:38, and then we're going to do some exploratory data visualization in plot and with an import. So get some coffee. I'll see you again in 5 minutes, 9:38. All right, welcome back. 5 minutes goes by really fast. Okay, so hopefully you got some coffee or a snack or just got to walk around for a bit. Welcome back. We are going to be continuing right from Marcasado, which we had created and named. And just as a reminder, make sure in this wrangling that you did in this SQL cell, make sure that you have named the output here. So make sure that you've named this Marcasado. If you want to check and make sure that that's available, you can insert a JavaScript cell and then just call Marcasado. And you should see that now we have this array of objects that exist for us to use in our JavaScript data visualization, which is what we're doing now. All right, so we're going to be continuing with Marcasado. And now we're going to hop into exploratory data visualization. So we have the variables that we want. We have the names that we want them to have. Next step is to start exploring it, usually in graphs. Oh yeah, I'll go ahead. Thank you for the reminder, David. David asked if I could paste that code for the SQL right into the chat. So there, so it's doing this as two pieces. As a reminder, the key is also available. It's linked at the top of the notebook that you're working in for session 3. So if you click on the key and have that open another tab, then at any point you could copy over code from the key, which will match exactly what I'm doing in my notebook here. So that's another option. If you're finding that you get an error and want to make sure it matches the key I'm working from. Okay, so now let's do some exploratory data visualization. I did want to show one chart type that I think can be useful. You'll see this a lot with meteorological data that's measured over time to explore seasonality. We could also do like season plots with lines, but we are going to make a heat map of sea surface temperatures. But we could also use this to explore any of the other quantitative variables that are in our data set. I'm not going to start from scratch though. We could absolutely write this from scratch in a JavaScript cell. But what I'm going to do is I'm going to use an observable plot snippet from the add cell menu. For those of you who are joining for the first time for this workshop, Observable Plot is a JavaScript library built on D3 by the team that built D3, but that adds a layer of abstraction so that we can more quickly create or get started creating some common chart types that we would want to make. But you could also like completely customize and extend and add interactivity to your observable plot code. So I'm going to start from the add cell menu, I'm going to search for a cell chart. This is what we're going to use to create a heat map when the fill color of the cells are dependent on a value. And that's what we'll call a heat map. So I'm going to select cell chart and I see that a code skeleton using observable plot is automatically added to my notebook in a JavaScript cell. And this uses a built-in data set that's already in observable. So this is a functional example where if I run this by pressing like shift return or pressing the play button in that cell, then what I can see is this nice heat map. This is also using temperature data. But this is pulling from a built-in data set called weather. We are going to switch this over. So we use our Marcasado data, and then we're going to do some customization on this. So the first thing that I need to do is instead of saying I want to use this subset from the weather data as my data source, which is that first argument within plot cell, is I'm going to switch this to, nope, we're getting our data from Marcasado. The next thing that I'm going to do is for X and Y, I'm going to give it what I want to be what's along my X-axis, which we're going to have be the month pulled from our month column in Marcasado. And then on the Y-axis, we're going to have the year, which is also pulled from that month column, which we're going to still use this get UTC month, but we are going to then switch to get UCT full year to get the year from that month column. So here on my x-axis, instead of pulling from a date column, which is where the date was stored in that weather data set, Our column that stores dates is called month. If we look back up at our Marcasado, notice that this date column is stored as month. So this is saying, I want to pull from the month property. And this is on the x-axis, I want to pull the month. So I just switched this to get UTC month. So months by number, this is going to use 0 indexing for months from 0 to 11. That's going to be on the x-axis. And then on the y-axis, I am also going to pull a piece from that month column, but I'm going to pull the year. So I can use get UTC full year. And then the fill, instead of temp max, which was in weather, we're going to use a property that exists in our Marcasado array, which I'll use SST, which is our sea surface temperature. And now we have a start for a heat map of our sea surface temperatures for each month over the years. Now we only have 5 years here, but you can imagine if you had really long-term ecological data, then you could start seeing patterns in like changes in seasonality and see if there are shifts in some of these either climatic variables or other ecological variables, but also like heat maps are great for any other field where you have categories that you would want to break things up by an X and Y axis bin, but then you want the fill color to depend on some quantitative variable. So here, let's do some customization, which we haven't done a ton of, but little plug, keep your eyes out. We'll send reminders. Later on in the year, we're going to have a course specifically on Observable Plot. So make sure you come back for that. Other classes to look forward to too that I'll mention at the end. But here, let's go ahead and do just a little bit of customization. So this is where I've defined the mark, which is my cells, and the fill color for that mark. But what I want to do is customize this in a few ways. First, I want to, it's kind of weird to have this comma format for years. So I'm going to convert that tick format. So it's just 2013, no comma, for example. And also along the x-axis, I want this to actually have a month abbreviation. So I'm going to add, after I have defined the marks, I'm going to add a comma. And then I'm going to say, okay, for my y-axis or for my y component of my chart, here's the ways that I want to customize it. I want the tick format to be updated to not have a comma, so just this 4-digit year format. And I'm also going to say, just because I think it looks kind of cool, you can adjust like whatever you want to. Margins, inset, padding, how many ticks you have, tick format, angles, so you have full control over customization here. The next one I'm going to say, and I'm going to do this on the x-axis too, is I want the padding between these cells in the y direction to be 0. So this just gives it, the cells still exist, but there's no gap between them vertically. So those are the changes that I'll make on the y-axis. On the x-axis, I'm going to say I also want there to be 0 padding. Notice when I add that, now I can see that there's no breaks in the x direction. And the last thing that I want to change about this is, instead of having these months where January is 0 and December is 11, instead, I would rather that these show the actual month name abbreviations. So here I'll use tick format and then this really cool option, plot format month. Notice that there's also format month, format weekday. These are really great helper functions to make my life easier. And if I just use plot format month, then I can see that it's converting these month numbers that are 0 indexed to the month name. So we can see here, and I can also add a tooltip here. You could have also created this in the chart cell and then continued customizing. But if I add tip true, then I can see, and that's right in the mark, then I can see that on hover, I have an automatic interactive tooltip, which is super nice. But what we can see, and this reflects like what the authors are saying is happening, is they say, okay, there's this hot and humid, or hot and moist range. And remember, this is just sea surface temperature. We got a whole bunch of other variables that are informing their description. But we do tend to see like, oh, the sea surface temperatures in January and February and March and December Those are the warmer values. And then right around the middle of what they're describing as that cool, dry season, June, July, August, then we see much cooler sea surface temperatures. And if I wanted to change this to another variable, like let's look at photoactive radiation, then I can see that that also aligns, that I also have higher photoactive radiation in those hot, moist months, lower in cool, dry months. But if we look at something like air pressure, so let's see if I mean pressure. So if we look at mean pressure, then we'll see the opposite. Then we tend to see these higher pressures in those cool, dry months and the lower pressures in those hot, moist months. Now, you might ask yourself, like, well, I could type in these different variable names. Could I actually just like add an interactive radio button and toggle between them? Absolutely, yes. We're not going to do it today. In previous sessions, we had seen how to use observable inputs to create a little widget that we could customize and then pull those different variable names so that when they were selected, a different variable would be plotted. So we could quickly make this interactive so that we could toggle between those variables. All right, so we made our cell chart. You could update this however else you wanted to. But this again is looking at variables one at a time, and kind of a lot of the emphasis today is going to be on like, well, when we have like multi-dimensional data with a bunch of variables, how can we see a lot of information all at once across variables? And one thing that we did last week, but I want to show another iteration of it, is importing a pair plot. And so we imported a pair plot, which is just a matrix showing relationships and distributions when you have multivariate data. So this is what the notebook looks like that we're going to be pulling from. As a reminder, you can import any named content from other notebooks that you have access to in Observable. So imports gives you this really quick, light way to access, reuse, and build on content from the community. But here, for example, there's this nice pair plot, this nice matrix that Phil has made at Observable that includes both the chart, but also this interactive widget above where you can choose which variables from your data set actually are showing up in this grid that's created. All right, so what we're going to do is this chart is expecting data called data. So if it's expecting data that's called data, then how can we reuse this when our data is called Marcasado? A thing that we did last week was we just made a copy of our data called data and then fed that into this plot matrix function that this uses. But what we're going to do is use a new tool, which is really awesome, which is import with, which allows you to say, hey, I know in the original thing, it's expecting data called this, but in my notebook, I want to use that same content, but I want to use this name of thing instead of what it was originally expecting. And that allows us to avoid like making copies of things, using the names that are the same as whatever the original author used. So here's just an example where I'm saying I'm going to import that plot matrix, which comes along with the visual matrix that's created and also the interactive widget with, and this is the part that we haven't done before, where here you can say with, instead of just data, I want you to expect Marcasado instead of data. And that's importing from the slug of that notebook where that content exists that we want to reuse, where the name is plot matrix. So here I can then, instead of using plot matrix data, if I then use plot matrix, and I just think this is so cool, with Marcasado, then I instantly have access to this beautiful and useful interactive chart that Phil has made. And again, replacing the expectation of data as the source name with my name, Marcasado. So here, what I'm doing, so here we can take a look at whatever variables we want to. So we have a bunch of variables here. what I want to do is we want to start, this is useful because we have like these 8, 9 climatic variables and C metric variables. What we're really going to be asking a question about is if it looks like, based on all of these variables combined, does it seem like there are distinct differences between this hot, moist season and this cool, dry season? And if we start looking, instead of having color, notice you can also choose the color, how color is mapped. If we choose that to season, then we can really start seeing some distinctions here. So we see distinctions in the distribution of the individual variables, which are shown on the diagonal. So we can see, for example, that mean pressure tends to be lower towards in that hot, moist season. Photoactive radiation tends to be higher. Those orange bars are shifted towards higher values in that hot, moist season. We could see sea surface temperature is higher in those hot, moist seasons. So we can see the distributions for the individual variables, but we can also see the relationships between variables. And breaking it up like this by choosing season as the what color is mapped to, we can really see like, oh, it looks like across these different variable relationships, there does seem to be some distinction between those hot, moist, and cool, dry seasons. But we are still looking at both of these, like we're still looking at pairwise relationships here. We're either on the diagonal looking at an individual variable's distribution, or in the scatter plots, we're looking at these pairwise relationships. So this is always one variable plotted on a scatter plot versus the other at the intersection of where they exist on this data set. But we can see some trends here, like that mean pressure seems to be inversely related to photoactive radiation. We can see, for example, here that sea surface temperature looks like it is positively correlated with photoactive radiation, for example. So we could start looking at these individual pairwise relationships. But what we really want to do is ask ourselves, like, can I get a bigger picture, more holistic view of, like, in this n-dimensional space that my data exist in, how do these compare between seasons across my many variables that I have in the data set? And this is where we're going to switch over to principal component analysis. All right, I'm going to read this definition of principal component analysis, and then we're going to pretend like we're whale sharks, and then I'm going to show a real world example, and then we're going to do the thing. There is not linear algebra in this presentation. There are a lot of caveats, but this is meant to be a kind of conceptual introduction to what principal component analysis, or PCA, is and how can it be helpful for us. All right, I'm just going to read this. Principal component analysis is a technique for analyzing large data sets with a high number of dimensions. For us, that's a large number of variables, which increases the interpretability of data while preserving the maximum amount of information. It's kind of like bang for your buck approach to trying to interpret high dimensional data. Formally, it's a statistical technique that reduces the dimensions of a data set, or can allow you to reduce the dimensions of a data set, which transforms your data onto a new coordinate system. And that new coordinate system's job is to explain as much about the data as possible, but in a fewer and more manageable number of dimensions than the initial data might have been in. Many studies will use just the first two principal components, because we're really good at like thinking about and visualizing things in 2D, in order to plot data that started as this like many variable data in a space that we can handle, which is in 2 dimensions. And that allows us to identify clusters of closely related data points. It also allows us to explore relationships between variables. So this is the kind of formal introduction to what principal component analysis does. Now let's pretend like we're whale sharks. I promise that this is related. I think this gives us a nice setup to thinking about what principal component analysis is actually doing. I would like to ask you to humor me by pretending like you are this whale shark, where this whale shark is currently oriented in this Cartesian coordinate system where its elongated mouth, which is mostly in the horizontal x direction, is again like kind of horizontally arranged. So this is like a perpendicular whale shark. So if I pretend like I'm this whale shark with my whale shark mouth, then what I would ask you to do, you can pretend like you're a whale shark. You can do, I can't see you. I'll just imagine that there are 41 people on the call pretending like you're a whale shark, which is great. Now what I'm going to do is on the next slide, I am going to show a krill swarm. And this krill swarm is probably not going to be like perfectly in line with my whale shark's mouth right now, but whale sharks can move, which is great. What I'm going to ask you to do is when I show the next slide, think or act like a whale shark and think about which direction you would turn your whale shark face to get as much of those krill as possible in a single pass. Ready? You're going to nail this. You can't go wrong. All right. So here's a krill swarm. So if you are a whale shark who is originally swimming with your perfectly horizontal mouth and you're approaching this krill swarm, then you are going, I could see that my screen is, reversed. So you are going to tilt your whale shark head to get as many krill as possible. You're going to you're going to rotate your face, right? So that when you pass through this, you are getting as much krill as possible in a single pass. Now, you're not going to get them all, but this brings up some really key ideas and intuition that you already have about what principal component is actually doing. Principal components analysis is saying the original coordinate system that we are showing our data on is not necessarily the coordinate system that allows us to capture the most information about the data in the fewest dimensions. But we can always change that. Like I can change my whale shark face direction. I'm going to miss some of the krill on that first pass, but like I'm a very energy efficient whale shark. I'm pretty happy about getting like a lot of the krill in one pass. Maybe I'm like feeling good. I'm like, I'm going to come around again because there's some of these krill left over and then consider like, all right, on my second pass now, what is the best way to capture the most of the rest of the krill? And then I would rotate my whale shark head and maybe come at it from a different direction and try to get the most krill in the second pass from what's left over. But the idea with the whale sharks is that in whale shark speak, to get as much krill as possible in the fewest passes, because you don't want to waste energy, you're going to lose some of the krill, but you can rotate your whale shark face on each pass to catch as many of the krill as possible. But in data, what does this mean for us? In data, what PCA is saying is to get as much information about like high dimension data with a bunch of variables in a smaller and more manageable number of dimensions, we can define a new coordinate system. We can rotate the way that we are projecting this data. And the way that we're going to do that is by defining this new coordinate system is made up of our principal components, where the first principal component is the one that explains the largest variance in the data. So that's like us being like, I will rotate my head this way to get the most krill on the first pass. That's kind of what the first principal component is doing. Followed by the second principal component, which will explain the second largest possible variance in the data. And then it will continue for as many different variables as we have is the number of principal components. But because the like first principal components, like 1 and 2 are usually the ones we visualize, will contain as much of the information, explain as much of the variance as possible with our data, allow us to see in a fewer number of dimensions as much information about the data as possible in a way that we can actually start to interpret when we start with data that's really large and that has a lot of variables. So let's look at a toy example, and then I'm going to show a real example, which will give us an indication of how we're going to actually visualize this. So let's say we have some mock data where this is data for like age, hours watching TV, and hours spent studying. And for conceptual purposes, let's say that this is kind of like the shape of a football, I think is the easiest way to think about this. So this is a shape of a football. What principal component analysis would do is say, like, instead of just sticking with this original coordinate system for my axes, instead what I'm going to do for that football is I'm going to define a different coordinate system based on my principal components, where the direction of those are called eigenvectors. That's the most into linear algebra we're going to get today. And the variance explained is described by eigenvalues. So if you have a football and you want a data that's in a football shape, then you can imagine that the most variance explained might be an axis, or an axis that is created, a principal component that goes through the two endpoints of the football. So we'll say that is my first principal component. And then, okay, then we can ask, well, then what's the new axis? What's the new coordinate, principal component 2, that explains the second most variance in my data? And that's PC2. And then you would have this for 3 dimensions, you'll have 3 principal components. For 10 dimensions, you'll have 10 principal components. But what you usually end up doing is saying, okay, well, we're really not good at visualizing anything above 3 dimensions. I think it's arguable that even 3 dimensions, like 3D charts, are also really hard to consider. So instead, let's just plot our data. And we'll see later, we'll also plot our reprojected variables just based on those first 2 principal components. So converting this highly dimensional data just onto my first 2 principal components. Now you should ask at this point, like, well, aren't I missing something? Yeah, we're going to miss some of the krill. But because the way that these principal components are calculated, they are PC1 is explaining the most possible variance in one direction. PC2 is explaining the second most possible variance. And then it only goes down from there, that we could potentially be seeing and containing a lot of information about our data in 2 dimensions, which is way more manageable for us to try to think about than like 10-dimensional data or 20 or 30 variables trying to plot that in space, which I can't even think about what that would look like. All right. So this is what PCA is doing, is it's taking data that has a bunch of variables, it's defining a new coordinate system where those new coordinates are trying to explain as much of the variance as possible, decreasing from PC1 explains the most variance, PC2 second most, 3, 4, 5. And then we're usually plotting that in 2 dimensions on what is called a biplot. So what can that look like? I just want to show an example. This is a standard example of PCA that you'll see a lot of times in examples. This is a data set that uses characteristics of wines from different wine growers in Italy. And there's these 13 different variables, like the alcohol content, phenol content, the hue, optical density. I don't know a lot about wine, so a bunch of other things I don't know about. But trying to consider like how these 3 wine growers differ across all of these variables is hard if we just have a grid of 13 by 13 pair plots. How can we visualize these all in the same place that still contains a lot of the information that exists in the data, but in a number of dimensions that is manageable for us? PCA lets us do that. And what we'll create and what we'll make today is what's called a PCA biplot. And what a PCA biplot shows is the reprojected values of our data onto PC1 and PC2, onto these new principal components that we have determined capture the most and second most variance in our data. That's what the dots show here. And then arrows that are showing the reprojected variables or the loadings of the variables. So when we look at it like this, and you can see here, we see principal component 1 explains 36.2%, PC2 explains almost 20%. So if we have 56% of variance in data explained in only 2 dimensions, that is showing us a lot about the data that actually has 13 variables to start with, but mapped into 2 dimensions that we can make sense of. When we look at it this way, we can really see that like there are these clusters for the 3 different growers. So there's this coral, orange, and blue dots represent the different growers. Those are the original values projected in this new coordinate system. And then we have these arrows, and those are indicating the principal components are linear combinations of all of our different original variables. And these show the loading. So you can think of this as like larger arrows that are more aligned with the direction of a principal component kind of have more importance to that principal component, a larger loading on it. So we can also start looking at like correlations between variables, like hue and optical density here seem to be pretty correlated if the angles are close. Malic acid seems to be negatively correlated with hue and OD as they map onto PC1 and 2. So we can start getting information about both the observation values in this new coordinate system and also the variables in this coordinate system plotted on a biplot. Let's go ahead and do it. All right, PCA is awesome. Yeah, so it gives us this really cool way to take data with a bunch of variables and use dimensional reduction to try to get that or visualize that in a smaller number of dimensions that still retain as much information about the data as possible, which is cool. All right, hopping back to my notebook, let's go ahead and do this thing. So in principal component analysis, we are using the ml.js JavaScript library again. Again, we get it. We covered this in day 1 of the workshop. We use require to pull in the pieces or methods from that, including PCA. And the other thing that you already have included in the notebook is this is a couple of functions from Chris Palmeyer's hierarchical clustering. Here I'm using imports again because I think they're awesome. That's going to scale the data for me, centered at 0 with a standard deviation of 1. And another nice helper function that he created, which will just be helpful in returning the outputs of PCA in a nice format for us by getting it into a nice 2D matrix. So the first thing that we're going to do here, all right, put our coding hats back on. Cool. We were whale sharks. We kind of know what we're doing, getting as much krill as possible. We know we're sacrificing some. Now we're back to our Marcasado data. So instead of wine characteristics or krill, now our multiple variables are these different atmospheric and ocean variables. We're going to create a scaled version because we don't want the weightings for the calculations for the eigenvectors or the eigenvalues to depend on the units that these are measured in, which is really what like the actual value of any data point depends on. So we're going to scale this first. So I'm going to make a new version called Marcasado Scaled. Hopefully everybody's back in their fork. And I'm going to use, well, first what I'll do is I'm going to do this in 2 steps. I'm going to create a version of Marcasado that only contains those quantitative variables, so that excludes season and month. And then I'm going to scale those quantitative variables. So here, as a first step, I'm going to say, starting from Marcasado, I'm going to use map. As a reminder, map is going to iterate over each element in an array, returning the output of a function in a new array. So here I'm going to do something new, which is to exclude 2 columns. So this syntax is going to look a little bit different. So here I'm going to start, notice the syntax here, by saying the input parameter for this function is an object. So that's what I'm writing here. Just like when we had used map before, we had an object be the output of the function. Here we're saying the input is an object, and that object contains things called season, month, and then the rest of the stuff. So here I'm using the spread operator, this ... and that's going to say the rest of things that exist there. But all that I want, so that's the input. That's like the input parameter for this arrow function. And the output of that function is just going to be the rest of the things. So what this is going to do is actually exclude season and month from my output array. So here, when I run this, then what I've done is I've created a version of Marcasato where there now are only those 9 quantitative variables, mean pressure, all the way through sea surface temperature. So that's a cool way to exclude properties from objects as you're iterating through an array. But the next thing that we want to do is scale these. So we're going to use that function that we imported from that other notebook, from Christopher Palmer's notebook that we have access to. And I'm going to wrap this entire now subset. I'm going to wrap that entire thing in the scale function. Make sure you have parentheses on either end. And now I can see when I look at the data that those have all been scaled to have a mean value of 0 and a standard deviation of 1. So now I have my scaled data set. All right. Next step, though, is that the ml.js PCA function is expecting an array of arrays. It's not expecting an array of objects. It just wants the values for each of our properties with no property name. So that's what we're going to do next, is that we're going to convert our array of objects to an array of arrays, where each array in that array just contains the values in our objects. It drops the properties. Here's what this is going to look like. I'm going to create Marcasato array, and I'm going to start with Marcasato scaled, use map to iterate through each element in the array, which is at an object at that point. And then I'm going to use a cool method, object values, which is a function that automatically just pulls the values from an object and returns only the values in an array, which is exactly what we want. So running that, then I can see that now, instead of having, like if I compare these two, instead of having an array of objects where I have all of the different property names in objects, now each element of my array is just an array, and I only have those values. I don't have the properties associated with it. And once we have our data in that format, then we could perform principal component analysis. So here I'm going to call this Marcasato PCA, and I'm going to use ML PCA applied to that array that we've just created, Marcasato array. Okay, there is an option. We have already scaled our data because I think that's useful for plotting later on. There is an option right within Marcasato array. I'll just show you here to add scale true, and then it'll do the scaling right there. We already did it up above because I wanted to have a separate scaled version of the data, but you could do it right within the PCA method. Okay, so congratulations, you have just done principal component analysis, but like, I see a whole bunch of useful stuff for me here. Let's look at some things that can be really useful. So there are outputs from this ML PCA method that you can just call by their name. So for example, if I wanted to know how much of the variance in my data is explained by each principal component analysis, then I could use Marcasato PCA and then dot. And notice that when you use dot after this Marcasato PCA entity that we've created, that there's a whole bunch of things that you can call. But the ones that are going to be of interest to us are things like get eigenvectors, get loadings, get explained variance, get cumulative explained variance. So let's see, I'm going to just do get variance, get explained variance. So I'll do get explained variance. Remember to include the open and close parentheses at the end of that. And what does this show me? This shows me that with this new coordinate system that I've created that we're going to project our original values on, that 35% of total variance in the data is explained by that first principal component. Then an additional nearly 20% of variance in the data is explained by principal component 2. So what this tells me is like just with 2 dimension, and you can see that it goes down from there. Like by the time we get to the ninth principal component, 1.5% of variance is explained by PC9. But just with the first two principal components, we have nearly 50 or 55% of variance explained, which is pretty cool because that's like a lot of variance in our data explained, but in a way that we could consider much fewer numbers of dimensions. And we could also look at the cumulative variance. So Marcus Auto PCA, get cumulative. What's this one called? Yeah, get cumulative. Oh, I did PCS. That's why I didn't come up. Get cumulative variance. You could use tab completion there. And you could see, yep, that by the time I get to two principal components, 55% variance explained, almost 70 with three principal components. So we see that like we can retain a lot of information about our original data in a fewer number of dimensions by creating this new coordinate system with principal components. It's so cool. I think principal components is like very, very awesome and beautiful. All right. So now, and we could explore other stuff too, standard deviations. You could get the eigenvectors, you could get the loadings. So there's other outputs. But now what I want to do is go ahead and visualize this. I'm going to visualize it in a couple of different ways. First, we're going to create some nice tables of the loadings. So that's information about the loadings of different variables for our principal components. And second, we're actually going to reproject our original data points, our original observations into this new coordinate system so that we can plot our original data now on these first two principal components. So here, what I'm going to do is I'm going to use imports again because I think imports are awesome. Again, this is from one of Christopher Palmeyer's great notebooks, this one on principal component analysis. And in this example, what Christoph has done is he's actually creating just a nice table of the loadings, so these combinations of variables and how they're mapped onto the new PCs. So here I'm going to use import, and I'm going to import the view of, because this is going to make a table for me. So there's a view of component and loadings. So I'm going to import that method with, and again, I'm going to give it that Christoph's version is expecting something called food scaled because he had done principal component analysis on some food characteristics. I'm going to say ours is Marcus Auto scaled. And I want you to expect that instead of food scaled. And then I can give it this link, and I'll open this so I can send the link to you. So we're going to use the slug from this notebook of Christoph's. And that's what we're going to use here to actually read that in. So I'll go ahead. I'm going to copy and paste this entire import with statement into the chat. Hopefully that comes in one group. And this gets us both this loadings table, and this is how we're going to map our variables into our new principal component coordinate system. But also lets us use Marcus Auto scaled instead of food scaled, which is what it was originally created for. So now it's expecting Marcus Auto, that's what it's Marcus Auto scaled. So if I just do view of loadings here, this is so cool. Then I could see these different loadings for my different variables, 8 variables, I've been saying 9, excuse me. And then the loadings in each of the different principal component directions. And what we're going to ultimately end up doing is we're going to plot a vector. We're going to plot an arrow indicating the reprojection of our variables onto principal component 1 and principal component 2. So they're going to extend to the values of these principal component loadings. So for each variable, we'll have an arrow that extends from 0 to, on the x-axis, that PC1 value, and on the y-axis, that PC2 value. So that's how we'll do our variable reprojection. I'm going to do a similar thing with each of our observations. So we also want to visualize We also want to visualize our points, our original observations in this new coordinate system, particularly on PC1 and PC2. So we're going to do that by getting the scores. And luckily for us, Christoph also has a nice table for scores. So here, if I do import view of scores with, and then I'm going to do marcasado scaled as food scaled. This also requires the original data. So for us, that's just for the names of the properties. Marcasado as food. So this actually, in Christoph's example, expects the scaled quantitative variables, but also the original data, so that we can get the property names from. And then again, this is using that slug. So copying that slug within these quotation marks. This gets me pretty close, and I'll go ahead and copy that import view of too. So here is that second import. And let's look at the view of scores, because sometimes what will happen in other notebooks is maybe it's not exactly what you want, but it's pretty darn close. And that was the case when I looked at the output of Christoph's scores method here. So in the scores method, let's just go ahead and take a look. So if I look at view of scores here, this has almost everything that I want, except for it was expecting a variable called name, and we just don't have that. For us, that would be month. So we don't have that variable in our data set. So I'm going to just do one more wrangling step, but this does tell me for each of the months in my data set, so the order is maintained here, then what would be its location in this new coordinate system for each of these principal components. So like all of these principal components values, that defines in this high dimensional space in my new principal components where one of my observations is. Again, we're only going to look at PC1 and PC2, but that's what this is giving us. But I do want to have both the actual month here, and I want to also add seasonality, the season, that hot, moist, or cool, dry column, so that I can show that on my biplot too and start exploring some clustering. So here we're going to do one more wrangling step, and then we're going to create our PCA biplot in Observable Plot. I'm going to call this scores combined, because this is just going to combine the scores that are existing here, scores with, and for this code, what I'm going to do is I'm going to get everything from that scores array that exists, but I'm also going to add to it the month. I'm going to give that the column name. We could exclude name and just call it month, but I'm going to call name the month. And then I'm going to pull the season based on the index number from marcasado. So here, the way that this is going to look is within map, I'm going to say iterate through each object in the array and also give me the index. So starting at 0. And I'm going to return a new object in this array that gets created, where I want to keep everything in the existing array. So I use that spread operator, ... d just says return everything from that object. But I'm also going to say I want name actually to be a variable that contains my month. So here I'm going to say I have that index, which will start at 0. So for marcasado object I, like row I, then I want to access the month property. So just running this just to see what we're getting here is what I have now the name stores each of those dates pulled from marcasado, and I still have all of my principal components for each of my observations reprojected into my new space. But I also want season here, so I'm just going to do the same thing that I did for name. I'm going to say I also want to have a property season, which pulls from each of the elements in marcasado and returns the value from season. And those are just where we had made that conditional case when statement in our SQL query, which seems so long ago, in our SQL query where we had added that new column season, which contains either hot, moist, or cool, dry. And now I have the name, which is our month, the different principal component values for each of my points, and I have the season. All right, now we are going to create a PCA biplot that includes, a biplot includes both those original observations reprojected into that space, and then we are going to add our variable loadings, which will be our arrows that tell us something about variable importance to the PCs and how they're related to each other. So that's what we're going to do next. And actually, let's take another 5-minute break. So let's go ahead. We'll take a 5-minute break. We'll be back here at 10:33 to make our biplot. We'll wrap up with some collaboration examples, and then I'll describe the assignment a little bit. All right, I'll see you at 10:33 to wrap up the course. All right, welcome back. We're in the home stretch and we got only fun left. So what we're going to do to wrap up PCA is we're going to create a biplot showing our original data and variables reprojected into this new coordinate system. Then we're just going to demo. I'm going to demo with Robert just really quickly how you could work with a teammate in a notebook. Then we'll wrap up by describing your assignment task and how to submit it. Okay, so we're going to create a PCA biplot. We're going to be using Observable Plot, and we're going to combine different marks here. Yes, there's a request to copy this last cell that I did. Hopefully that comes across in one thing. There you go. So we're going to be combining different marks and combining data from different data sources, which is something that we haven't done before. We're going to get our reprojected points on PC1 and PC2 from scores combined. So we're going to make a dot mark that shows the locations of our scaled observations on PC1 and PC2. And then we're going to create an arrow mark that shows the loadings on PC1 and PC2 of our original variables reprojected on PC1 and PC2. And then we're also going to add text to label those variable arrows. So we're going to build this piece by piece in Observable Plot. We're going to write this from scratch, which we've been using snippets so far. But let's go ahead and write this out. So I'm going to start by initiating my plot. I'm going to have an outer set of parentheses where this is initialized, and then an inner set of curly braces. And within these curly braces is where I'm going to do everything to create and customize my chart. I'll add my marks. I can add the more global options for my chart, but I'm going to start by specifying my marks. And again, those are going to be, we're going to add a dot for my points, an arrow for my variables, and then text to label those variables. So we say, here are the marks that we're adding, and then square brackets. And then within this marks section, this is where we're going to add all of the marks and tell it what data to use and what variables we want to be plotting on these axes. So the first thing that we're going to use is we're going to use this scores combined data, which combines on my principal components the locations of my reprojected original observations. So I'm going to say the first mark I'm going to add is a dot mark. So I say plot dot. I want to get the data. That's my first argument from scores combined. And then I give it in, I have a comma, and then I have curly. Then I'm going to tell it what my X and Y variables are. Those are going to be my PC1 and PC2 here. So if I look at this array, PC1, PC2 are going to be my X and Y axis variables. And then I can have the fill change on season, which again will allow us to start exploring on my new principal components how and if things cluster. So here I'm going to say on the x-axis, that value is based on the PC1 value for an observation. On the y-axis, the PC2 value. I'm going to have the fill color change based on the different categories in season. And I can also update things like the radius of my point. So I'll say the radius of this point, I want to be 4. I'll scroll down so you can still see the code. But what this is showing me is now on my first 2 principal components, the locations of my original observations. And what's interesting is that we can see this is capturing, again, as much of the variance in the data as possible in just 2 dimensions, is that we see this pretty noticeable clustering where we have, I'll add a legend here so we can see it. I'll add a legend associated with the color. So we can see that there is some separation between these hot, moist months across those different variables and those cool, dry months in my data. And as a reminder, we're not capturing everything here, but over 55% of variance in our data is captured just within these first 2 principal components. So we can still pull apart like some like major takeaways about clustering and patterns and similarities, where the more similar or the closer observations are in this space indicates that they're closer overall across those variables in this new space. So now we got our dots. Cool. That shows us the scores. Next, we're going to add the arrows showing our reprojected variables. So our variable loadings on principal components 1 and 2. So I have a comma after that dot mark, and I'm going to add another mark that is plot arrow. And we're going to pull this from a different array, from a different data source, where our data source here that these are in is called loadings. So I have my different variables, and then we are going to have each arrow for each variable extend from 0, 0 to, on the x-axis, PC1, and on the y-axis, PC2. So that's what we're going to write next. So here I'm going to say start from loadings for this mark. I'm going to have, and then you give it x1 and x2 for each arrow. So I'm going to say x1 starts at 0 and x2 extends to the value in the PC1 variable. Then I'm going to say y1 is 0 and y2 is going to extend to the value in the PC2 variable. And what you can see show up once you've defined the starting and endpoints of that variable is our reprojected variables, where again, variables that are closer to variables in the horizontal direction, like maybe these two, those are having more importance or larger loadings on the first principal components, versus those that are vertically oriented here are maybe informing PC2 or more important to the second principal component. Now these are a little bit small. We're going to do some just like scalar scaling of these just so we could see it a bit better. So for each of these, I'm gonna define a new, there's like recommendations about scaling here. I'm going to create a new scaling factor, which I'll call like 5. And then I am just going to extend the X and Y values by multiplying it by a scaling factor there. This is just making my arrows bigger for the sake of making it clear, like the directionality here. What you really want, which we're not doing here, is since those can be on different scales, you want to have the left and bottom axis be scaled based on the scores usually, but then you'll have a second top and right axis based on the values for those variables. So for those arrows, we're just using the scaling factor so we could see those a little bit easier. But right now we can't really see what those are. These each represent a variable rescaled. So here, what we're going to do is we're also going to add a text mark. So right after that plot arrow, I'm going to add a comma. I'm still within my square brackets for marks. And I'm going to add a text mark. So I'm going to add plot text. This is going to get pulled from loadings again. That's the data that describes the loadings for my different variables. And I'm going to, again, give this the values for X and Y, which is where that text should be located. You can nudge these things. You could customize it. You could set a fill color and an outline color for your text. We'll just put them on there and see what this looks like. So I want each of these labels to be in the X direction. I want it to be at the X value for that principal component for that variable. So PC1 and I'm also going to apply my scaling factor to this just so it maps on to what we're already showing for the variables. On the y-axis, I'm going to similarly say that this should be at the value of PC2. Again, scaling this using that scalar value. And then the last thing that's essential for this text mark is to say, like, what is the actual text? Because there's a bunch of variables here. We could have it show like the values of things. but we want this to be showing the text that exists in the variable column, which if we look back at the loadings data, that's how this is stored in this array that we're using, is as variable. And running this, what we'll see is that now we have our scores and our loadings. So we have both our original observations, our scaled observations, and our variables as they look reprojected based on my new coordinate system and labeled with these different variables, which is pretty cool. So we could see things like, for example, it looks like photoactive radiation and sea surface temperature are highly correlated, which makes sense. Very sunny, hot days, higher sea surface temperature. And it looks like observations for months in that hot, moist season also tend to have values on PC1 that are more towards those larger values or larger loadings for that principal component that seems to be largely influenced by PAR and sea surface temperature. Whereas if we look in the other direction, mean pressure, that we can see that these cool, dry months, those tend to maybe fall more along the lines of like lower pressure, which is what we see, that there's this negative correlation in our data from our pair plot between like sea surface temperature and mean pressure. And we should never look at these in a vacuum. Like if I go up to my pair plot and look at the relationship between sea surface temperature and pressure, which is this grid square, I can see there's a negative relationship. And that we can see reflected. It is normal to see that these are slightly different. What you're really interested in when you're looking at a PCA biplot is not like absolute locations of things, but relationships of things in space. So you'll also see, I actually showed an example. I had recreated this in R just as like validation, and it's actually just rotated a bit. So the absolute location in this new coordinate system is usually not what we're interpreting. We're interpreting the relative locations of things to each other, like how are points clustered in space relative to each other, not necessarily just like on some absolute scale. All right. So now we have our PCA biplot. Again, we could customize this. This isn't showing everything. What's key about PCA is, yeah, we're not in these two principal components, in this two-dimensional biplot, we are not seeing everything about the data. But what we have done is we have, from 8 variables, we are now able to view and retain as much as possible about the data in a number of dimensions that is really more manageable for us, both to think about and to visualize. Yeah, sorry, and I will move down to the code. As a reminder, the key is also available. So if this didn't turn out the same way as mine, then we also have the code available in the key, which is linked at the top of the notebook. All right, so this lets us start from like complex data, whether that's like patient responses or blood chemistry or biogeochemistry or financial data that is too many dimensions for us to try to consider all at once. To be able to reduce that to a number of dimensions that we can think about while still preserving as much information about the data as possible with these new principal components. Okay. So now I'm going to switch back over to the slides to wrap up today. Okay. No, I'm not going to. The first thing that I wanted to show you, I almost left Robert hanging. One thing that I wanted to remind people of is there's a bunch of different ways to share. So you can sit back, take a breath, hang out. I'm going to remind you of some cool stuff. There are a bunch of different ways that you can share, export, things that you create in Observable Notebook. I want to highlight those because that's a pretty common thing. Any named cell, so like I just gave this biplot a name, we can embed elsewhere. You can also download it. So notice that I can like download an SVG of this plot, which is great if you're doing like additional design. You can also download a ping. So you can download a file. That's one thing. We've already seen that you can share a notebook by updating the permissions and then just sharing a URL, which is amazing to have like an interactive notebook or dashboard that like all you have to do to publish and share it is share a URL. Is pretty awesome. We also saw in the last session that you can embed things. So for any, remember, and the key here is named. So if you see a grayed out embed option, first thing I would check is if you named it. But here, if I click on the cell menu, I can choose embed. And then I can choose, oh, so this still requires, there's a notebook privacy thing here. But here, if you have made this not private, then you could copy the URL and you could go ahead and then you could embed that elsewhere. And there's other options for how you could embed. And that includes with both the actual visualization and an input. So you can maintain interactivity when you do an embed, which is really cool. And the widget comes along with it if you select it. So that's another way. But another thing that I wanted to show you today is that we can also just collaborate right in Notebook. So instead of being like, I'm going to like, maybe in other tools, you're like, I want this person to be able to edit this. So I'm going to save it. I'm going to commit. I'm going to push to GitHub. That person's going to pull it. They're going to make edits, do the same thing, push it back. Then we have the same version again. One thing that's really nice about working in Observable Notebooks is the ability to collaborate right in one place with simultaneous multiplayer editing. So I'm going to go ahead and show you that. So here, I'm going to hide my face so you can see what I'm doing. I'm going to go up to change the permissions so that Robert can join me in the notebook. So I'm going to choose share. Heads up, this is also where you are going to change the permissions when you submit an assignment so that I can see it. So you'll choose to make your assignment fork that you work in public view unlisted, which means it's not searchable, but I'll be able to see it. But what I'm going to do here is I'm going to let my whole team view or edit this notebook. And then I save those changes. Make sure you press save. And then I can send my collaborator, Robert, that link. And what I see is that now that he has that link, Robert shows up as an avatar in my notebook, which is awesome. So Robert has shown up in my notebook and I can follow him. So if I click on Robert's avatar, then this spotlights Robert. I'm not touching my keyboard right now. I can see that this takes me to wherever Robert is working, and I can see that Robert is now making this a bubble chart where the radius of my point is actually based on the value of principal component 3, and the symbol differs based on season. So, and we could work back and forth, and I could, I could change this. I'd be like, oh, actually, I want this to be PC4. Now we're both working in the same place. And another really cool thing about this for the communication wrap up is that we can leave comments for each other. So I can go up to my notebook and I can add a comment and I can say like, hey, Robert, can we update the color scheme? Which I don't think we're going to do today, but then the authors of this notebook will get a notification. They can respond. This means we can be working in the same place at the same time, no wondering if we're all working in the same version, having discussions about our data right in the notebook, which is a really, really awesome way to communicate with your team members, with stakeholders, with your managers, so everybody can really participate in one place without having barriers of maybe having to learn some new tools to actually do that communication and tinkering together. All right. Thank you, Robert, for showing collaboration here. Now we'll do our course wrap up. All right, everybody. Round of applause. You made it through all of the coding examples that we're going to do, which was a lot. We did like multiple ways of accessing and importing data from local files to remote files to making a database to importing from other sources. Wrangling in JavaScript, Arcaro, SQL, data table cell, visualization, and observable plot from the chart cell to snippets to writing it from scratch. We did modeling with the ml.js package for linear regression, k-means, and principal component analysis. And we learned a bunch of ways that we can communicate with our notebooks, from sharing the notebook link to adding collaborators, to embedding things, to publish them out elsewhere, to downloading, which is really, we covered a ton. We covered a ton in 3 sessions. So now, if you've been participating and you want a certificate, which we encourage you all to do for this course that you could share, there's an assignment that we are going to post like right now. It's ready to go, where what you'll do is you will fork the assignment just like you've done for these follow along sessions. So you will fork the assignment and then you'll work in your fork. To submit in the assignment, it's pretty like detailed in explanation. You are going to share the link for your notebook from your fork in a Google form with us. That's how we'll get it. So make sure that your notebook setting is updated to public unlisted. Otherwise, you'll get a message from me that's like, hey, I don't have access to your notebook, and then you'll have to change the permission. And it covers methods really closely that we've walked through in this workshop. So make sure to check the keys. There shouldn't be like curveballs in this assignment. And please ask questions in the Observable Community Slack Learn JavaScript channel. That'll be the easiest way to get a hold of us. We're really excited if you enjoyed this workshop series. We have existing courses that also have all open materials on like intro to SQL, intro to JavaScript data wrangling and analysis, introduction to data visualization and advanced data visualization, all available on YouTube, and all our resources and notebooks are available. And upcoming, we are super excited. We're going to have courses this fall coming up on BI and Observable Plot on its own, and an introduction to D3, which is one that I am super excited to take. So thank you so much. I want to say a huge thanks to Robert and Wayne for their help with this course behind the scenes. You are awesome. But really, like, thank you so much to everybody who participated, engaged in conversations during the course. Make sure to reach out if you have questions or want to follow up, and we would love to see you on the community Slack. So thank you so much for being here. Have a wonderful day, and I look forward to getting your assignments and sending you your certificates mid-August. All right, due August 4th. Certificates will be out mid-August. All right, bye, everybody. Thank you.